Hi everyone, I'm Anatolii, and today we prepared a short lecture and we will talk about haptics, and in particular we talk about my earlier work on exploring feature-based learning for data-driven haptic rendering. I'm a member of scientific staff at University of Gent and I live in Belgium, and I'm preparing this short lecture for Dnipro State Technical University. This title that you see over here is actually the title of my work and the papers that we publish in IEEE Transactional Haptics. Down below you can see the link to the paper where you can read it in more details. I will briefly go overview what we're going to talk about. First, I will introduce a little bit about haptics. And then we talk about what is data-driven approach, how we deal with the data processing. We talk about the framework of the methods that we come up with, and some of the results that we have. So what is haptic technology? Well, haptic technology basically refers to technology that renders sensation of touch. You sense this sensation of touch through your skin as one of the largest organs in your body. And generally, humans have five sensor modalities. One is audition, another one is vision, sense of smell, sense of taste. Well, haptic is just one of those senses that we try to digitize, process, and work with. Some of the typical devices that you can see here is, for example, on the right there is a device that we all have currently in our pockets, and it's a basic cell phone that delivers a vibration, for example, in a silent mode when the phone rings. Here you can see a haptic feedback device embedded in Apple phones, so that delivers a more sophisticated vibration signal to your skin. And aside from vibration, you can also deliver to our muscles. For example, you can deliver a sensation of force. So you can see here on the left typical device that we work. It's a commercial device. And that's what we use in our laboratory. For example, you can see here, so it's a basic 3 degree of freedom or a robot arm, or 6 degree of freedom if you count this 3 DOF feedback on the wrist and effectors. So these devices, you can see, consist of 1 motor, 2 motors, 3 motors, and also 3 encoders. So the motors are here to deliver sensation of force. So basically by computing proper torque, and encoders here are to measure the actual position of this end effector. So for example, if we track the position of an end effector at any point, we can deliver, for example, force. We can think of the scenario where we have a virtual wall here that we're trying to cross, and once we start crossing this virtual wall, we start providing force. Well, how do we provide force? One way is through simulation. And the simplest way is to consider a spring, or force equal minus stiffness multiplied by displacement from the virtual wall. This is again what we use in our lab, but this is done, for example, this deliverance of force done through simulation. In our work, we don't want to work in simulation, but we want to collect the actual real data from the real object. So how do we do that? Well, first we slightly modify this device and attach a force sensor to actually measure the real interactive forces that we observe when we touch the object. So here you can see, for example, our basic setup. It's a basic data collections setup, and it consists of automated sampling station. You can see here 2 force sensors. This is ATI Nano 17, and what you cannot see is basically the same 2 haptic devices that I saw. This is done in order to collect bimanual information, not just simple manual, but just to collect the bimanual compression forces and investigate how we interact with the real forces, and how to even collect information in a bimanual sense from, as you can see here, it's a deformable object. So briefly, I will show you a simple recording how it works. So you see compression started, and this is at 0 phase, and now the phase between one tooltip and another tooltip starts to change. This is actually to fully digitize the deformation space. So this process is repeated multiple times, once per contact point, and on each face of the object we have 72 contact points. And in general, to sample information from one object, it requires roughly 8 hours. In our database, we have 7 or 8 such objects that we fully digitize, and what we most importantly do, create a model or a function with which we can deliver what we just recorded. So you can think of it as a digital record of the touch sensors and replay device. So once you record it, for example, you can record the haptic properties or even deformable properties of the object and transmit it, for example, via the internet to the distant location where you can replay such forces. So data processing is relatively complex, well, because it involves, as you can see in the previous slide, I explained that we record significant amount of information, and this creates a problem when we try to generate a model. So what we come up with is slightly in a way of how to reduce dimensionality of the problem, how to reduce amount of data that we can use. So for this purpose, we want to find some sort of a low-dimensional abstraction to each of the data vector. Once we find this low-dimensional abstraction, we can work on a data that's significantly smaller in size than actually data is recorded in dynamic. Note that for haptics, we typically record every second around 1,000 points. Consider this is a bimanual setup, we record a lot more information. And depending on the way we sample, if you sample just 2 bimanual probes facing each other, or for example they're shifted, so there are even more information that we need to record. And we do this through automated recording in an automated way to make sure that we fully digitize the objects that could be replayed through the model and deliver it to the user, for example for him to feel the forces that we record. When we look for low-dimensional abstraction, we first have to come up with some sort of a way of working on those abstractions, or for example working on the features. So each data type, for example, that being force, that being displacement, that being velocity, has its own feature, and this feature will be in the future processed in a more efficient way. So we have response features, for example, for force. You can see we converted from high dimensional real-time vector to much lower dimensional feature. And then explanatory feature also, for example, for displacement, velocity. You can think of it as a predictive variable. So this is input and this is output. And we try to model relationship between the input and output, both on the feature and later in time domain. I will show you in details how we do it in time domain. The same for the features. We try to come up with an abstraction to the real vector. And here we can actually achieve a significant reduction in information. So what we want to learn further is a non-linear relationship between features. So we don't look at the data, the massive amount of data that we record, but we look at their features. So we find the non-linear relation between features, and then we figure out how can we deal with based on this information with the vectors in time domain or information in time domain. So the next step, for example, after we learn this abstraction and find the relation between response features and explanatory features, we go and build a global model. This global model will be used to deliver haptic sensations. In the next slides, you can see how we obtain response features. The response features consist of forces that we record. I showed you previously how we record information that we want to convert to our real force vectors. We want to convert to the force features. And as you can see, the dimensionality of the vector significantly reduced. How do we do that? Well, we look at what we recorded. So, for example, this is our amplitude of displacement, or the amplitude of force. And this is a displacement. So you see it behaves very nonlinear. So as the probe contacts the object and start displacing the object through the sensorized probe, we can see force increases. And this is for compression, synchronous compression at 0 phase. So it's just basically like closing a gripper. And then when we're reaching maximum displacement, the tooltip retracts, and then we obtain such a step. So this is recorded, as I said, at phase equal to 0. And on the other hand, we process this information and observe what happens in the force spectrum. What is nice about processing information in Fourier domain is basically we know this is oscillatory type signal. That you remember we record our data set. It's essentially oscillatory data points that we record. And here we convert it in a frequency spectrum. It's through Fourier transform, and you can see here our appearance of the first harmonic, second harmonic, third harmonic, fourth harmonic, etc. So this why nice to use frequency spectrum? Well, frequency spectrum and dealing with information, processing information in frequency spectrum have nice connection to rheology. Rheology is the study of flow of soft matter. So we deal with the form of material. There is a field that works on this field. So we have a nice connection and kind of interpretation of what if each of these harmonic means in a frequency spectrum and in reality. So the rheology is a field that tries to find different aspects of the real material by interpreting activation of each of the harmonic. So here you can see just some basic fundamental frequency, modal frequency, phase, displacement, amplitude, displacement rate. These are the predictors to a response feature. So next slide, you can see how we deal with other information. For example, so this is during compression at zero phase, and this is roughly when you saw the recording. This is how the plot force versus displacement looks. For example, at phase pi, for example, 180 degrees. And of course, when one of the tooltip is stable and one hand can move, so we also have to record this sensation. So this recorded in oscillatory manner from phase 0 to phase 2 pi. And of course, you can also see force spectrum on each of those harmonics amplitude for each of those phases. So you can also notice that with increase of pi, the leading harmonics shifts its location in a frequency spectrum. There is a little frequency or a spectral leakage, but this can be handled through more data collection in oscillatory way. So this is how we obtain the response feature. We just take out points. Of course, it's a frequency spectrum, so there is a real and complex. Here you can only see the amplitude. Next, what we observe, we record the same shape of the material, but a little bit harder. For example, you can see the difference in the profile. So this can definitely indicate to you that this is a soft material. You see it behaves in a nonlinear way as the probes come very close to each other. But this one is more difficult. We stop our recording when the force reach up to 7 to 8 newtons. So this is material that we deal with. It's a medium stiffness material, and the same behavior for the phase equals 0, pi, and 2. And we also observe force spectrum in this fashion. So this is how we convert again response features. And the hardest materials that we have in our library, you can see here 3, but we sample, I think, up to 9 objects and observe their converted force spectrum. So, for example, this object, if it's recorded at the highest speed that we have, contains 330 points, but in the frequency spectrum, it just contains few points. So this is a result that we can use, and then we can build our, for example, feature extraction, and this is an integral part of the data reduction. Explanatory feature, as I outlined, is basically displacement, the velocity in time domain, or for example, amplitude, phase, and you notice phase is found throughout the correlations. Phase is basically different. This is compression, and this is one of the two handle moves, and the other one stops. So, for example, this motion, one stopped, and then one moves, and through the medium of the object, you can feel a feedback on your other hand. And this is our 0 compression, and then all the way to phase 2 pi. And of course, we also have a component for the velocity. So in general, we describe a lot of those really coarsely and with just a few explanatory variables. So you can see here gamma, you can see here phase, and you can see here omega to indicate in abstract ways the velocity. So now I'll briefly go. This is how we deal with the initial data processing to record massive volume of, to reduce massive volume of data through feature engineering. It's called field in machine learning to something more manageable. To overview of our data-driven haptic modeling, it looks like that. So we recorded our haptic data, we stack them up as a vectors, so there's a lot of vectors, and more important, there's a lot of more information in each of those vectors. So we want to find a corresponding kind of data compression for each of those vectors. You can see here is reduced. But more importantly, this reduction doesn't tell us anything. We just model the relationship. We cannot infer any information that will be useful in time domain. So what we do, we want to select in a greedy way, we want to select the components of each of the features, so that if we select this one, we can predict, if we build our nonlinear model based on, for example, of those 3 features, the rest of them can be predicted successfully. So this method called, a basic way, it's called greedy selection. So we first start with the one with the highest error, or randomly assigned. This is the first vector. And then we select 2 until we reach certain threshold, and if we reach this threshold, we select a second vector, a third vector, etc. So idea is to reduce this amount of the number of vectors, and this correspondingly reduces the number of vectors in time domain. And then I will briefly, so in time domain, once we collected this short amount of vectors, this is already more manageable to work with, and from this we can actually construct a real data-driven model. And what is data-driven haptic modeling or data-driven modeling? For example, you collected a lot of data. You want to find some sort of a modeling layer or model that explains each of those points, that you come up with this type of model. So we use, for example, to model such interaction between the collected data point, we use a radial basis function. I can talk more about the radial basis function, but I think it's out of the scope for this lecture. And this radial basis function, more importantly, they're very data greedy. So we require to precisely collect enough information so that radial basis function would provide us with accurate results. So here you can see how we more in details how we do select each of those components in a feature space, or how do we model this feature space. So you can see each individual model. This constructs through radial basis function approximation. We start from the first component or in a predictive feature, right? So to explain the shape of this, if we stack them up and put them as a plot, is very simple. It's almost linear. So it's sufficient to use 1 or 2 vector. This is an abstraction, not the real case. So 1 or 2 actual vectors, right? We start from the random and then we add additional one. So this is a critical vector. So select, and we select all of the components for this vector. So this vector is already now identified as important one. That helps us with the reconstruction of the data. We move to the second components of the feature vectors, right? And the shape of this is a little bit more complicated. We build a model, each individual vector for each individual vector component. And you can see here we add extra force vector. So you can think of it like you need more points to reconstruct to model certain nonlinear behavior. And as nonlinear increase, if we go down frequency spectrum, we add more and more vector. Here it's abstracted by my view. So once we've done this, just here to show you how it looks, to remind you how it looks in a time domain, or so to show how it looks on actual data curves. So first we start with the feature extraction via fast Fourier transform, as I mentioned. Recorded data converted to Fourier spectrum. We got our response feature. We construct our explanatory feature. Now we start modeling. As I remember, I saw that the first harmonic typically behave very simple if you stack them up. Well, that's true. That actually this is an actual recording. So for the first 13 vectors, I think it's stacked. First components of the 13 vectors. You can see to reconstruct this information just needs 3. Here we don't even need, we already can predict this information. That's why we don't add any data point to our radial basis function model. And here is the final point that we add in order to reconstruct. You remember each of those components once they pass through each of the components of the vector in a feature space, would result in certain number of corresponding time domain vectors or time domain signals. This is a compression signal, this is a 2π signal, and this is almost something in the neighborhood of the phase equal to pi, phase difference between tooltips that compresses the object. And you can see here is the last one that we add. So this one is already more manageable. For example, from gigabytes of data, we reduce just pretty much nothing in the modern world for the modern computing technology. Next, each of these oscillatory compression, we create separate model to extract a certain number of points. And you can see here, what we do, we accumulate all of these selected points and build a global radial basis function. So this global radial basis function will be used during the rendering. And some of the basic results. As you can see here, we have a recorded force signal. Remember, it's reminiscent of what I showed you on the second or third slide. So this is what we recorded. This line, this is recorded, and this is computed via other method that we used before. And you can see it's almost matches. Feature-based learning, you can see this is what we just come up with. So this is a conventional method that shows the error in Newton. Remember, 1 Newton error will be very noticeable, depending, of course, on the magnitude of the signal. But here we can see the error between the real and computed using our feature-based learning significantly reduced. Here also abstracted by the view error behavior depending on the number of frequency harmonics that we choose to process in our data set. And here it's basically, it looks like this. If we have few harmonics in our data set, then the reconstruction will be really bad. We increase it, and we stop at certain point. We so far reduce the stopping criteria for number of harmonics that we use in our work, basically by hand tuning, by just looking how far we can go and how much information it makes sense to reconstruct, because at some point harmonics stops explaining significant amount of information, start explaining noise and other disturbances. So in the end, we use this to deliver haptic sensation and haptic rendering. This model is really short and compact and can be transmitted to a distant location. For example, for you to use it via, for example, teleoperation is another subfield of haptics. And I think this will be the end of my short overview lectures. Thank you for listening. And if you have any questions, please let me know.